Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at something called empirical and molecular formulas. All right, this is something that's really not too difficult. It's just a bunch of mole conversions that we should be familiar with by now and hopefully getting better at. Usually year after year, students say they really end up enjoying empirical and molecular formulas because it's really satisfying once you actually do get the right answer. Especially if you do it the right way, everything just kind of falls into place and it's really nice. So I'll walk you guys through how to do a couple examples and then you'll be able to practice some either on your own or in class. So let's define what an empirical formula actually is. An empirical formula is simply a mole ratio of each element in a compound. Okay, so substance with a mole ratio of 1 mole of nitrogen to 2 moles of oxygen will be NO2. That's the empirical formula. It's the simplest mole ratio that you have for a molecule. So it's the lowest whole number ratio. So another example is if you have 1 mole of nitrogen for 2.5 moles of oxygen, it's not going to be N1O2.5. That's not a whole number ratio. You need to have a whole number ratio. So for that case, it would be N2O5. If this is what you had here. If you had 1 mole of nitrogen for every 2.5 of oxygen, you have to multiply through by 2 to clear out your decimal to end up with nice whole number ratios there. So if it's not in whole number form, make it into whole number form. Multiply by 2 or by 3, whatever you have to do to make it happen. So, a couple practice problems with this. So how do we determine an empirical formula from masses? So we're going to do a couple lab simulations or even some real labs where we actually do stuff like this and figure out empirical formulas from some data. So a compound containing chromium and chlorine. Okay, so it tells us what our elements are. It's separated by electrolysis, which is a chemical means of separation, right? It's a flashback to the beginning of the course. Electrolysis separates compounds, chemical method of separation. It separates it into 23.1 grams of chromium and 47.2 grams of chlorine. What's the empirical formula for the compound? So what I want to figure out is the lowest whole number ratio for this. So that's our hint here. We're looking for a mole ratio. So you're probably going to have to do some sort of mole conversion here. And that's step number 1. There is this little flowchart, mole rainbow type thing that you guys have in your notes. You want to figure out where you're starting. We're starting here. We have the mass of each element. We want to get to empirical formula over here, right? So we have to go from the mass of each element into moles of each element. So it's just doing a mole conversion. Then get to your mole ratio, right? See what's the ratio between everything. And that will give you your empirical formula. So let's do that. We have to convert into moles of everything. So in order to do that, we need to just simply do some mole conversions. So let's set them up here. You should have room on your note sheet to do this. We have 23.1 grams of chromium and 47.2 grams of chlorine. So set up your factor label. And I'll just go through this part relatively fast. It already pops up on the screen. The molar masses on here might not be exactly what's on your periodic table, so I may have made this using a different one, but they should still be really, really close, and you get the same idea. So 51.97 grams of chromium, okay, in 1 mole of chromium. That'll give us 0.444 moles of chromium when you convert 23.1 grams into moles. You do the same thing for chlorine. 35.45 grams of Cl. Grams of Cl cancels out. In 1 mole of Cl, you get 1.33. Okay, so this looks really weird, right? Your ratio is 0.444 chromium to 1.33 chlorine. What do we do here? So if we go back to the mole rainbow thing, we're right here. We have the moles of each element, right? I want to get to my mole ratio. You have to divide each mole amount by the smallest number of moles. So that's a really important step here. All right. So let's divide through by the smallest number of moles to get my ratio, right? Because the 0.444 to 1.33 just looks really weird. It's hard to figure out. So divide 0.444 by 0.444. You get 1. And you divide 1.33 by 0.444 and you get 3. Look how nice that comes out. So you're always, always, always going to have something become 1 mole at the end, right? because you're taking the lowest number, dividing it by the lowest number of moles. So you're always going to have something that comes out to be 1. And then some other stuff that might be 1, it might be some other numbers. In this case, it's 3. So the mole ratio is 1 mole of chromium to 3 moles of chlorine. So the empirical formula is really easy to write. It's CrCl3. Simple as that. You're finished. That's the lowest whole number mole ratio for this substance. So you can name that. We should be able to name that after our nomenclature unit. Chromium has more than one charge, right? Chromium's not in groups 1, 2, or 13. So you write chromium. You have to tell me what the charge is on that, and Cl3 would be chloride. Chloride's a -1. There's 3 of them, so it should be chromium 3 chloride, if you're writing the name for that. So that's what we separated in this situation. Okay, next one. It's really not much different. Minor detail in the beginning that's different, though. A compound is 26.6% potassium, 35.4 chromium, 38.0 oxygen by mass. What's the empirical formula going to be? So again, what's the empirical formula? It is the lowest whole number mole ratio. So what we have to do here is do one initial step first. I don't really know what my mass of my sample is, but ultimately it doesn't matter because I know what the percent composition is of that. So whether I have 2 grams, 50 grams, or 100 grams, it's always 26.6% potassium, 35.4 chromium, and 38.0 oxygen, right? So what I can do to make my life as easy as possible is pretend you have 100 grams of your compound. If I have 100 grams of my compound, I just pretend that, then it's really easy to figure out what the mass of each of these things would be to convert it into moles. So I have to convert these percents into moles somehow. Well, the assumption I'm going to make is I have 100 grams of my substance. So then I have, assuming then I have 26.6 grams of potassium, 35.4 grams of chromium, 38.0 grams of oxygen. I just convert to moles. It's going to be the lowest whole number ratio anyway, so it's going to work out really nice. So if you're given percent mass composition, use a sample size of 100 grams. Okay? Then you have the mass of each element. Then just follow the roadmap and get to your empirical formula, which is what we have to end with. So there we are. We got to get to empirical formula. So let's knock it out. 26.6 grams of potassium, 35.4 chromium, 38.0 oxygen. So we're pretending we have 100 grams of our sample. So we would have this many grams of all these things. So a couple quick mole conversions. Again, they might differ a little bit from your periodic table, like potassium's 39.10. There's an extra sig fig in there. But anyway, cancel out grams of potassium. You end up with 0.680 moles of K. Do the same thing for chromium. Okay, 51.97 grams of chromium. Cancels. So we end up with 0.680 again. Just happens to be that same number, no big deal. 38 grams of oxygen. Convert into moles of oxygen. 16.00 grams of oxygen. Gives you 2.38. Okay, so students, they tend to forget the next step, even though it's like a really, really important step. And they get really confused, like, well, it's 0.680, 0.680, 2.38. What ratio is that? You have to remember to divide through by the lowest number of moles. So divide through by 0.680, you get 1. Divide through by 0.680, you get 1. Divide through by 0.680, and you get 3.5. Okay? Feel free to pause the video to make sure you have all these written down properly so you can follow this procedure for your future examples. So this even looks a little bit weird. The mole ratio is 1 to 1 to 3.5. So let's write that out. K1, CR1, O3.5. Weird, right? So just if I went back a bunch of slides where we had the example of, I think it was N1, O2.5, we converted that into, we multiplied through by 2, we made it N2, O5, right? We're doing the same thing here. What can I multiply this by to give me whole numbers the whole way through? I can multiply through by 2. So I'm going to have K2CR2O7. These things should, for the most part, end up as something like you're familiar with. So K2CR2O7 makes perfect sense. Potassium is a +1, and then Cr2O7 is dichromate. It's a -2, right? So you need 2 potassiums to balance out your -2 charge on dichromate, and your name is potassium dichromate for this substance. Okay? That's empirical formula. That's all you got to do for those. You only have 2 options. You start with your grams, if that's given to you in the problem, and go to moles, divide through by your lowest number, get your ratio, or you're given percents, and you have to just pretend you have 100 grams of your sample, make all those mass, go to moles, ratio, done. Molecular formulas basically do the same thing with one additional step. So let's take a look at some vocab here before we do some example problems. A molecular formula is simply the number of atoms present in a molecule of a molecular compound. So nitrogen dioxide is NO2, that's the molecular formula. Carbon dioxide is CO2, it's the molecular formula. So covalent compounds, things that start with nonmetals, are made of molecules, right? Just a terminology difference here. Ionic compounds, even though sometimes I'm talking too fast and I say molecules of NaCl, it's really not true. Ionic compounds don't really have a molecular form because you don't just have like one of them, okay? Like molecules of CO2, you have one of them, and then you have an attractive force, and then there's another one. So they're separated. Ionic compounds really aren't. Like you have NaCl, 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 this repeating like crystal lattice structure. So what we say is one of these chunks, okay, one of the pieces of that repeating pattern, we call that a formula unit, okay? So we say the formula for sodium chloride is NaCl. We just write 1 Na and 1 Cl, right? In reality, it's NaCl, and they just keep going one after the other after the other. They make these really cool crystal lattice structures. Different ionic compounds make different ones. We'll talk about that in AP Chem a tiny bit, but that's just a difference in terminology I want you to make sure you're aware of. Okay, so what's the molecular formula for carbon dioxide? So molecular formula is simply the number of atoms present in a molecule. Well, carbon dioxide has 1 carbon and 2 oxygens present. So the molecular formula is CO2. What's the empirical formula? Remember, the difference here is the empirical formula is the lowest whole number ratio. Well, is CO2 already in the lowest whole number ratio? Yeah. So in this case, it's CO2. Okay? So if the molecular formula is already in the lowest whole number ratio, then it's also going to be the empirical formula. All right? But if the molecular formula was not in the lowest whole number ratio, then they would differ. We'll see some examples coming up. Here's a perfect example. So we're looking at glucose. Here is the molecular structure of a mole of glucose, or just a molecule of glucose, I should say. So we have how many carbons? 6, right? C6, H, how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. O6. 1, 2, 3, 4, 5, 6. All right? So the molecular formula is how many atoms in the molecule. Easy. C6H12O6 is the molecular formula. The empirical formula will be different here. What should the empirical formula, the lowest whole number ratio, what should that be instead? Well, that's going to be CH2O. Okay, so this is the lowest whole number ratio, right? That's my empirical formula. This, my molecular formula, doesn't have to be in the lowest whole number ratio. Okay? So how does this all work? Step 1 on this chart in your notes. Determine the empirical formula for each of the above compounds. So I give you the molecular formula in the column here. And then there's a percent composition over here that you'll do next. But let's find the empirical formula first. So molecular formula of ethyne, C2H2, what can I reduce that to? Well, I can reduce it to CH, right? What about C6H6 for benzene? Well, I could do the same thing, CH. Okay? So notice how ethyne and benzene have the same empirical formula, but a different molecular formula, right? Methanol, CH2O, looks like it's already in its lowest whole number ratio. So that's the empirical, CH2O. It's already reduced. What about ethanoic acid, C2H4O2? Can I reduce that at all? Yeah. What will it be? It'll be CH2O. Look at glucose. C6H12O6 is CH2O. This is really neat because methanol is a really, really flammable, very toxic, very dangerous type of alcohol. The empirical formula is CH2O. If you just expand on that, like if you make that ratio larger and you have C6H12O6, it just becomes sugar, right? So you go from a toxic, extremely dangerous, flammable alcohol to sugar just by multiplying your empirical formula a couple times, okay? So step 2, determine the percent composition for each compound. If you go through and figure this out using the percent composition process that you looked at a couple lessons ago, you're going to see that this is a little sloppy here now. Let me erase some of this for you. Okay, because all of it popped up on the slide. For ethyne and benzene, the percent composition is the same. Okay, because your empirical formula is the same. Look at the last three. Percent composition is all the same. Even though your molecular formula differs, it's the same empirical formula. So as you look at the completed chart, we end up with similar empirical formulas having the same percent composition. So just because something's 40% carbon, 7 hydrogen, 53% oxygen, doesn't mean it's methanol. It could be any multiple of methanol, all the way up through glucose or even potentially things larger than that. Okay? Next thing I want you to focus on, molar mass. Methanol is 30. I multiplied everything by 2 to get ethanoic acid. My molar mass doubled to 60. Well, now look, I multiply CH2O by 6, right, to get to glucose. Well, look, 30 times 6 is 180. So all these molar masses are multiples of the most basic reduced one that you have. Okay, so that's something important to know as well. A couple other examples, really neat. Ethyne is C2H2. It's called acetylene gas as well. It's used in welding. Styrene, C8H8, is those little styrofoam packing peanuts. Same empirical formula. Empirical formula is CH and CH. Two different substances. Same thing with the one I just talked about. So you go from methanol all the way up through glucose. It's the same empirical formula, CH2O, but different molecular formulas and different items, which is pretty cool. Okay, so one last time here. Notice that when the molar mass doubles, the molecular formula doubles. And we already said with methanol and glucose, you're going from CH2O to C6H12O6. You're multiplying by 6. So you multiply by 6 for your molar mass. So, a couple practice problems. The empirical formula is the lowest whole number ratio, is NO2. The molar mass, though, is 138. What's the molecular formula? Okay, here's how you figure these out. If you have the empirical formula, it's NO2. You want to figure out what is the molar mass of that. What's the molar mass of my empirical formula? So I have this chart down here. My formula is NO2. My molar mass is 46 grams per mole. Okay? It tells me that the compound actually has a molar mass of 138. What you want to do is compare 138 to 46. and see what the multiple is going to be, just like we did here. Glucose has a molar mass of 180. Methanol has a molar mass of 30. It's a difference of a multiple of 6. So if the molar mass gets multiplied by 6, the empirical formula gets multiplied by 6 to give you your molecular formula. All right? So the molar mass is 138. My empirical molar mass is 46. What's my multiple there going to be? So what's happening there? 138 and 46. What do you have to multiply 46 by to get 138? 3. So once you multiply the molar mass by 3, you have to multiply the empirical formula by 3. And that gives us N3O6 for that molecular formula. So 2 practice problems for how to do this. And then we'll do more on your own for homework and some in class. So a compound has an empirical formula, CFBRO, molar mass 254.7. What's the molecular formula going to be? So let's go to what we did on the last example. We want to go to molecular formula. Here's our mole rainbow thing. So once we have our empirical formula, you have to look at what the factor is between the empirical and the molecular. So the factor is right here. You take the molar mass of your compound, divide it by the molar mass of your empirical formula to see what your factor is. The last example, the factor was 3, right? So you did 138 over 46 gives you 3. So we knew our factor was 3 to do the problem. So here, to find the factor, we do the molar mass of the compound over the molar mass of the empirical formula. So the factor is going to be molar mass of the compound, 254.7 grams. Molar mass of the empirical formula, you add up 1 carbon, 1 fluorine, 1 bromine, 1 oxygen, and you get 126.9 approximately. Factor is going to be 2. So what do you have to do then? If your factor is 2, you have to take your empirical formula, multiply it by 2 to get your molecular formula. So in this case, CFBRO times 2 is C2F2Br2O2. All right? So that takes care of really quick and easy practice problem. One more. This is as long as it's going to get right now, okay, for a situation like this. So determine the molecular formula. So you only need to figure this out if it asks you, and it is right now. So find the molecular formula of a compound where the molar mass is 695, and it has 26.7% phosphorus, 12.1 nitrogen, 61.2 chlorine. 3 elements in here. All right. So let's go to the mole rainbow, and we are given a mass composition. We want to go to molecular formula. So we have to go the whole way through the mole roadmap here to figure it out. So we go through a lot of the same process. We have to get to the empirical formula first. Okay? We can't get to the molecular formula until we go through the empirical formula. So this, literally, the first 1, 2, 3, 4, the first 4 steps of this is a complete review of about 20-ish minutes ago, at the beginning of this lesson. Okay? So let's go through and get the empirical formula. And then all we have to do is find our factor and go from there. So I'll walk us through it. We'll get over with. So 26.7% phosphorus. Let's pretend we have 100 grams of this. So we would have 26.7 grams of phosphorus. Okay, let's convert that into moles. So I'm going to cancel out grams of phosphorus and go to moles. Always work in terms of 1. So 1 mole of phosphorus is 30.97 grams. Go to proper sig figs and you get 0.862 moles of phosphorus. Okay, moving on, we do nitrogen. 12.1 grams of nitrogen. Cancel out grams of nitrogen, go to moles. 1 mole of nitrogen is 14.01 grams, and that gives us 0.863 moles of nitrogen. Last one, I have 61.2 grams of chlorine. Cancel out grams of chlorine and go to moles. 1 mole of chlorine is 35.45 grams. Gives me 1.73 moles of Cl. Okay, to find my empirical formula, I divide through by the lowest number. Divide by 0.862 for all of these. Gives me 1 mole of phosphorus, 1 mole of nitrogen, and 2 moles of chlorine. Okay, so I can get my empirical formula from this. It'll be PnCl2. All right, that's my empirical formula. Now what do? If I go back to my rainbow thingy, once I have my empirical formula, I find out what my factor is going to be and see what I should multiply by to get my molecular, if I have to at all. So let's find the molar mass of this empirical formula. So I add up a phosphorus, a nitrogen, 2 chlorines. That's going to give me a molar mass of 115.88 grams. Okay? That's for my empirical formula. So it clearly is not the same as my molecular, because my molecular molar mass was 695. So we'll do 695 grams per mole. Divide it by 115.88 grams per mole. And that's going to give me a factor of 6. All right? So I need to multiply my empirical formula by 6 to get my final answer. So I have to multiply this by 6. So that's easy to do. It was 1 phosphorus times 6 gives us 6 of them. So P6. Same with nitrogen. N6. Chlorine, there were 2 of them. Multiply that by 6 and you get 12. Oops, Cl12. Okay? P6, N6, Cl12 for your molecular formula for that. A little tedious, I guess, but honestly, not a difficult process. It's mole conversion, mole conversion, mole conversion. Divide by the lowest number of moles to get your ratio. And then if you're finding your empirical formula, you're done. If you're finding your molecular formula, find out what your factor is going to be, multiply your empirical if you need to, and get your final answer. Nothing should be really weird in terms of your factor or anything. Like you shouldn't end up with 5.2. Like it'll be a really, really nice, even, like whole number, or a decimal that's really, really close, like maybe 5.998 or something like that. Okay? So that takes care of empirical and molecular formulas. What you want to do is look at some of the practice problems that I've assigned. You can work through them. And if you have any questions or concerns or issues with that, we can talk about it in class. All right, guys. Thanks a lot.